All right, what we're talking about today is one more gas law, and it's going to be a little bit different than the ones that we've done so far, because how many of the variables are involved in each of the gas laws we've done so far? Two. And then there were two other ones that we just left alone. What we're going to start to do at the end of this week and then next week is combine more than two variables at a time, and eventually we'll get to the point where we have equations that involve all of the gas law variables at once. So we're taking the next step up from two variables at a time to three variables at a time. So today is the combined gas law, which is a combination of three of the other laws. So we take the equations for Boyle's law, Charles' law, and Gay-Lussac's law and put them into one equation. What was the equation for Boyle's law? P1 V1 equals P2 V2. So for Boyle's law, we had pressure and volume being multiplied. What was the equation for Charles' law? V1 over T1. V2 over T2. How about Gay-Lussac's law? P1 over T1 equals P2 over T2. So think about those three equations. In all three equations, in whichever ones it shows up in, was the pressure on the top or on the bottom of a fraction? Top, in all of them. How about volume? Top. Temperature? Bottom. So if you take those three equations, those three variables, and put them into one equation, it would make sense that the pressure and the volume are going to be on the top, and the temperature will be on the bottom. Those are the three that will be in this equation. We are still holding the amount of gas constant. We will add that one next week and do all four at the same time. And here's what your equation looks like. P1 V1 over T1 equals P2 V2 over T2. What do we need to remember about temperatures before we plug them in?
They have to be in Kelvin.
They have to be in Kelvin. Change them to Kelvin. And then as far as the other two things, units on both sides need to be the same. This is essentially the same thing that we've already done. We still have a before case and an after case. We just have more letters. The only thing that's changed with these problems is that there's more things to organize or more things to deal with. Speaking of the need to organize more things, there's three variables. You could also use this equation as any of the three minor gas laws that we already talked about, Boyle's, Charles, or Gay-Lussac's. They would work for any of those three. If, let's say, we get to the test and you forget what Boyle's law is, you can look at this one, the combined gas law, use this the same way. But because there's so many pieces, lots of information with these, if you have not been in the habit of making a list of what you have and what you're looking for, you may find that you need to start doing that. When you read these story problems now, there's going to be 5 numbers to sort out, 5 numbers to decide where they go, and you'll solve for the 6th missing thing. So you may find that you want to start doing that list even if you haven't been doing them up to this point. Not much goes with this equation other than practice, practice, practice. A gas has a volume of 800 milliliters at 23 degrees C and 300 torr. What would the volume of the gas be at 227 degrees C and 600 torr? What are we solving for? Milliliters. V1 or V2? V2. The rest of the information is given in the problem. V1 is 800. T1 is given as 23 degrees C. Add 273 to that, you get 296. And P1 is given as 300. Then it said, solve for the second volume. What would the resulting volume be if the temperature changes to 227 degrees C, which would be 500 K, and the pressure changes to 600 torr. Then you plug your numbers into your equation. Remember, for the test, this is the step I need to see. I need to see where your numbers go. And from here, it's just algebra. Cross, multiply, and divide, just like we've done before. Oh, I solved this one a little bit differently. You can cross, multiply, and divide and work the same way. I simplified all the things on the left and then divided these two things on the right. Works the same both ways, as long as you do your algebra correctly. How many sig figs should we keep? 4. Go back to the numbers in the question. All of them had 4. Depending on how many times you round during your work, you should come up with about 675.7 milliliters. Okay, ready for the next one? A gas sample occupies 3.25 liters at 24.5 degrees C and 350 kPa. Determine the temperature in Celsius at which the gas will occupy 4.25 liters at 150 kPa. So decide what we have and what we're looking for. What's the 3.25?
Volume.
Volume. 1 or 2?
1.
1. 24.5? Temperature. 1. 350? Pressure. 1. What are we solving for?
The second
Temperature 2. And volume 2? It's 4.25. Pressure 2 is 150. Don't forget to change your temperatures to Kelvin before you put them in the equation. Plug your numbers in. Make sure this is the step that you write down when we take the test. Once you get to this point, you can solve whatever way you're comfortable, algebra-wise. Cross, multiply, and divide might work best. Might be the easiest one to do on this one. Okay, out of the equation, you should get 167K. Look at it, that's K. And then if we need to change back to Celsius, we have to subtract 273, and you do get negative 106. We seemed kind of thrown off when you got a negative.
Yeah, but
it's possible to have negative temperatures in Celsius, right?
Yeah.
We had them all winter. Unfortunately, so don't let that throw you off just because it's a negative. 0.73 liters of nitrogen at STP is heated to 80 degrees C and the volume is increased to 4.53 liters. What is the new pressure in millimeters of mercury? What's STP stand for? Standard temperature and pressure. What's standard temperature? Okay, what's standard pressure? Well, if you don't know, look back on the chart. That very first chart we filled out. Standard temperature is 0 degrees Celsius, which would be how much in K? 273. Standard pressure is, it is 1 atmosphere, but what's the question ask us for pressure?
4 millimeters in, that's mercury.
Millimeters of mercury, so that better be the number that we plug in. What's standard pressure in millimeters of mercury? 760. So even though it may not seem like it at first, we do have all the information we need to solve this problem. We have the first volume. We know standard temperature is 273 K. We know standard pressure is 760 millimeters of mercury. The second volume is given as 4.53. The second temperature, 80 degrees C or 353 K. And we're solving for the new pressure. Plug the numbers into your equation. Solve for P2 however you like. Check your sig figs. If a gas in a rigid container has a pressure of 1.75 atmospheres at standard temperature, what is the new pressure when it's heated to 50 degrees?
Well, we know what the standard temperature is. 273.
Yeah, so we know we have a pressure. We know standard temperature is 273. We're being asked for a new pressure, and we're given a second temperature.
We're not even saying volume.
We're not given any volume. What's a rigid container mean?
It doesn't change.
It doesn't change
Volume.
volume. It doesn't change size. So if the size isn't changing, then the volume is the same. And if the volume's the same, do we need to include it in the equation? No. This is an example of how the combined gas law can also function as any of those three minor gas laws we started with. Here's what we have. What law does this look like then? This is Gay-Lussac's law. Because volume doesn't change, V1 equals V2, we could put that into the equation if we wanted, but think about math, if you have the same thing on the left and on the right, what happens to it? It cancels. So if the volume's the same on both sides, it drops out of the equation, we don't need it. And you could just solve this like Gay-Lussac's law. Here's the math to prove that the volume's going to drop out on both sides. You can see it cancels on the left and on the right. If you do your algebra correctly, you should get approximately 2.07. This comes out in atmospheres because that's what you put in.